All right, we started section 2.1, reasoning and logic last time. We had talked about what statements and negations were and quantifiers, which make things a little bit difficult. And kind of where we really left off was in the middle of truth tables and how we're creating truth tables for different kinds of compound statements. Conjunctions are statements with the word and in them, or the equivalent of the word and. Sometimes it will say the word but. We talked about that. And then disjunctions are statements that have the word or in them. And then we had done this truth table right here, I think was our last statement that we had done, right? Talked about how we create a truth table. All right, logically equivalent. Two statements are logically equivalent when they have the same truth value in every possible situation. And the way that that is written, let's say that you have the statements P and Q. Then the way that we write logically equivalent is we would write P, we would do it looks like a triple equality symbol, Q. Okay, so they're not equal. It just means that they have the same truth value statement in the final columns. The columns match if you were to create them. All right, so De Morgan's laws, this is two different ones here. De Morgan's laws say that the following two statements from the left to the right are equivalent to one another. In other words, if you have an and statement, P and Q, and you take the negation of it, okay, this is the first line, the negation of an and statement, well, it becomes an or statement. But it also becomes the negation of each of the individual statements. So it's almost like there's three pieces. There's the P, there's the Q, and then there's the symbol between them that's either the and or the or. And all three of them change. So if it was P, it becomes tilde P. If it was and, it becomes or. And if it was Q, it becomes tilde Q. And the same thing happens for an or statement. If you have an or statement and you negate it, you negate each of the individual statements, and then in the middle, you change it from an or to an and. That's how I create a statement negation for a conjunction or a disjunction.
So is it kind of like you're distributing?
It kind of feels like distribution, doesn't it? Yeah, it does sort of have that same feel to it. And what I want to show you on our next slide is I want to show you that these really are logically equivalent. Now, I'm not using the exact ones from De Morgan's laws, but a very similar one. So it says to use De Morgan's laws, I'm sorry, for example 3, we're just going to rewrite it, but in example 4, we're going to verify it. So example 3 says to use De Morgan's laws to write the negation of P and tilde Q. In other words, they want us to find the negation of this statement P and tilde Q. So this is going to be logically equivalent to what we write next. And we're going to go one piece at a time. What will the P become? Yeah, not P, or tilde P, right? The negation of P. What will be our next statement we write down, the next piece we write down? Right, the and will become an or. And then what will happen to our tilde Q? It'll just be Q. Now, this probably just feels like we're just manipulating symbols. And we are manipulating symbols. But it will work when we have those statements with actual language involved as well. So we're going to do one of those before we're all said and done as well. So have no fear, that's coming. We'll look at the language for it in a minute. Any questions on that example? Just the symbol part of it first. Yes, Ariel?
So in De Morgan's law,
Yes.
I don't know. Okay. It flips. I didn't see that.
Okay, that's all right. I definitely want to make sure you have it right in your notes, so I'm glad you clarified. Okay, so what we're going to do with example 4 is we're going to actually show that these two statements right up here that we just said were logically equivalent really are logically equivalent by this definition. We're going to see that they really create columns in a truth table that are equivalent, okay, that have the same T's and F's in the right places, or in the same places. All right, so what you'll notice, and we talked about this last time, is that every time you do a truth table, you're going to have a column for P and a column for Q. And if you had other symbols, like an R or something like that, you'd have a column for that too. We only have P and Q. Now, between both sides of this, I also have a tilde P and a tilde Q. So I'm just going to put them in there in that order because I know I'm going to need both of them eventually. So I'm just going to write a tilde P column and then a tilde Q column. Okay, is everybody good so far? All right, now this is like what you do when you're working with, say, algebra. When you see parentheses like you do on the left, you work from the inside out. So the things that happen inside the parentheses happen first, and then we will do the negation after that. Okay? So we're working just on the inside of the parentheses for now, and I have the P from here in my columns. I've got a tilde Q column. So the only column that I'm missing to have that whole expression inside is the whole expression, P and tilde Q. That's everything that's on the inside of the parentheses. I'm just writing down column headers for now. We will fill in the table, okay? And then the last thing, if we're trying to do a truth table for the left-hand side, is that I need the column that then takes the column I just created and negates it, the part that puts the tilde on the outside. That's what's missing. So my last column for the left-hand side would be to do tilde, P, and tilde Q.
So how do you know when to put the parentheses in?
I'm not sure I understand the question. Try again for me, Emily.
How do you know if we're going to see to left and P on that last column?
I'm just taking what I'm given right here and I'm writing everything down. So I already did everything inside here. I already did all of this. And I'm just working my way from the inside out. So the next thing that's out is the tilde P, which includes everything now. So I'm just going inside out, and it's just the next step.
There has to be a column for every part of the problem.
Exactly. There needs to be a column for every part of the problem. That's exactly right.
Distribute the tilde, whatever.
Right. Basically what we're saying is we're trying to figure out if this is really true. It's like I'm questioning it. I'm saying, if I do all the stuff on the left the way it's currently written, and I figure out a truth table for it, will I get the same thing as if I do it in the order that it's written on the right instead?
It's kind of like geometry with proofs.
It is much like geometry with proofs, yeah.
Yeah.
Now, if you look at the right-hand side, we also have each of these pieces already present in our truth table, right? I've got a tilde P column and I've got a Q column. So I don't need to like put them in the table again. They're already there. The only piece that I don't have is the combination of all of it with the or statement between. So I need my last column is I'm going to need a column that says tilde P or Q, because that's the last piece of this logically equivalent sort of thing we think is logically equivalent that I don't have represented right now in my truth table. Now, if this is really logically equivalent, what's going to happen is those last two columns, which represent, this is representing the left-hand side, right? And this is representing the right-hand side. If these are really logically equivalent, then those two columns, when I'm all said and done, should have the same T's and F's in the same places. So whatever's in that one that says right-hand side is exactly in the one that says left-hand side. That's what I'm looking for. That's what proves that these are logically equivalent, is that those two columns are the same. Okay? So that's what we're looking for as we work through it. Now, working through it from the left to the right, the P column, what will it always say?
True, true, false, false.
True, true, false, false. And the Q column, what will it always say?
False, true, false.
True, false, true, false. And you can do those columns whether you know how to even create all the headers across the top, right? Because they're always the same. The tilde P and the tilde Q columns are very easy to create as well. So when I create tilde P, I look back at the P column and I reverse it. So what should the tilde P column say?
False, false, true, true.
False, false, true, true. And what should the tilde Q column say?
False, true, false.
Okay, now let me make one comment right here, and I'll actually go back to the other diagram that we did last time. Notice on this diagram, there is no column for tilde P, right? Why not?
Because there's not a tilde P in the right.
Right. So don't just willy-nilly put tilde P and tilde Q in every problem. That's not necessary at all. It only needs to be there if it's a part of what you're looking for. This does not have tilde P in it, so I don't have a column for tilde P. The reason I have a tilde P and a tilde Q over here is because there are those pieces that are represented in the equation above.
And if for some reason there wasn't, like if the second part of the problem was a tilde P, you wouldn't
Right.
include it, right?
Exactly. If there isn't a tilde P on the left or the right, that is in the whole part of it, yes, I would not include it.
Even though there's a tilde outside the parentheses.
Correct. That's correct. Okay, Now our next column is where we actually have to sort of engage with some of our, processes for looking at these analytically. We need to go back and we need to look at the columns that it's referencing. It's referencing column P and column tilde Q. Okay, the ones that I just highlighted in red are the ones we need to be looking at, and only those two. When is an and statement true? When they are both true. And means they have to both be true. So the first row, I have a T in the left, or in the P column, and I have an F in the tilde Q column. So true and false gives me false. Second row, true and true gives me true. Third row, false and false gives me false. Fourth row, false and true gives me false. Okay. Now, the next column is easy. Don't make it more hard, more hard's not good. Don't make it harder than it needs to be. It's just the opposite of the column I just made. So the column I made right now says FTFF, right? So what will the column that I'm looking at, the left-hand side column, say? TF, what's next? TT. That's it. Don't make it harder than it has to be, okay? And if all we were doing was the left-hand side, we would be done with this argument, right? We would be done with the problem. We have one more column to do, however, and the column that we have left to do compares the two columns that we haven't already actually compared. It compares column tilde P and column Q, now the ones that I've highlighted in yellow. And they're comparing them with an or statement. So when is an or statement true? Either one of them or both, right, Amy? Yeah, either one of them or both of them are true makes an or statement true. So in yellow, I have true, false on the first row. What does true, false give me? True. The second row, I have false, false. That's false. The third row, I have true, true. That's true. And the fourth row, I have false, true. That's true. And we can see this column and this column match. So if I were to ask you to justify why this picture tells you that these are logically equivalent, you'd have to say that. You'd have to say the column that represents the left-hand side, or the column that is tilde P and tilde Q, whatever, is exactly the same true-false structure as the column that's the right-hand side. That's what shows they're logically equivalent. Yes, Hannah?
I'm confused. Could you go back to slide example 3? Because it's a part of this problem, but it's easier looking at that. Where did we add the parentheses to that row? Like, because we added the parentheses and we added the
We didn't add any parentheses. We just used the language that they gave us to write it. It says to write a negation of P and tilde Q.
Oh, okay.
So P and tilde Q is the question, and then I just put the negation symbol in front of it.
Okay.
Exactly.
Yeah.
And I just put the parentheses there so that we didn't think that the parentheses only applied to a portion of it. It's applying to all of it.
Okay.
Yeah. Okay. We need to do one where it's in words, though, and I think that's next, right? It says example 4. It's our second example 4, I guess. It's example 5 on my page. Does it say 5 on yours? Or does it still say 4 on yours? Okay. It does on my notes, too. But it does say 5 on my screen. So, use De Morgan's laws to write a negation of, it is not sunny and I will go for a walk. So, when you're encountering one with language, it's a good idea to identify the statements and the conjunctions separately. So the conjunction or the disjunction, whatever's between them, the compound part of it, the and or the or, is the breaking apart place of the two statements individually. So what we're supposed to do is we're supposed to negate, if you will, all three parts of this argument. So negating it is not sunny. What is the negation of it is not sunny? I want words. Yeah, it is sunny, right? It is not sunny's negation would be it is sunny. So it is sunny. What would you do to do the opposite, if you will, of the word and? You'd write or. And then the second statement says, I will go for a walk. I will not go for a walk. And that's exactly what a negation does. A negation takes the smallest thing that can go wrong and says that's sufficient for making the statement opposite of what you had. So if I said, it is not sunny and I will go for a walk. So imagine it's a cloudy day and I'm going for a walk. That's what that's saying, right? To pretend for a minute. It's cloudy outside and I'm going for a walk. What would be enough to make that not true? Well, it would be enough for it to be sunny. Or it would be enough for me to not go on my walk. Either of those pieces would be enough to make this statement false. And that's what this negation does. It says, well, the first part could be wrong, or the second part could be wrong. And we're writing it in words. And that's what De Morgan's law says happens. And that's correct. It's exactly what happens. Okay, there's one other type of, did I miss something?
No, it bugs me that it's not like a good sentence.
Oh, you don't like my sentence? Oh my goodness, I'm so sorry. I have created worse sentences. How's that?
I'm over it.
Okay, well, thank you. I appreciate that. That's grace extended right there. Thanks, Karina. All right, one other type of compound statement. We've done conjunctions, that's and statements. We've done disjunctions, it's or statements. And the last time we were together and we talked about the third type of statement, it was if-then statements. If-then statements are referred to as conditionals. A conditional statement is a statement expressed in the form of if P, then Q. It can also be read as P implies Q. And symbolically, it's a P and then an arrow and then a Q. That's what the symbols look like. It's got an arrow in it. The hypothesis is the if part of the conditional, and then the conclusion is the then part of the conditional. And sometimes the language that we start out with makes it look really funny. Like in English, we do funny things like this. We say, I will go for a walk if it is not raining. Well, the if part showed up at the end of the sentence, but it's still the if part. Are you guys with me? So in that sentence that I just said, the conditional part, or the hypothesis part is at the end of the sentence. So it doesn't always occur in sort of this P at the beginning, Q at the end, arrow in the middle. We have to be really careful about the language that's being used because we're weird and we speak English. Okay? We have weird things in our English structure that does that. I want to show you, here's my slide that I've got, what a truth table looks like for a conditional. So I'm going to show you first what it looks like, write it down, and then I'm going to give you an example to justify for you why it makes sense, or hopefully should make sense, that this is the way it should work. P, Q, and P arrow Q, okay? You all know how to fill in columns P and Q. It's not any different. And I'm going to use this argument to help us justify it. Okay, so this piece would be P, this piece would be Q. Okay? If I'm a mom, then I'm a woman. Okay. And I don't mean I as in me specifically. I just mean any person talking to you. Okay? So you're online talking with somebody who has some sort of a name online that you don't know if they're a man or woman. You got to start with that, okay? Okay, so their name maybe is Pat. Right? That's Saturday Night Live thing back from the day. I didn't watch it, but I'm told. There's lots of names that are gender-neutral names these days, right? You don't know what it is, okay? And this person says, in the first column, I'm a mom. If they're a mom, they're automatically a woman. That is a true statement, right? That's true. So this first row right here, if the person says, I'm a mom, and you assume they're a woman, you would automatically be right in assuming that. That is not a leap of faith. Logic statement. Okay? If the person says, I'm a mom, and you assume they are not a woman, you would be wrong. That just doesn't work, right? That would be false. And here's where things get tricky. If the person does not say that they're a mom and that they say that they are a woman, that could totally be true, right? There's nothing wrong with that possibility. In fact, most of you in this room would fall in that particular category. Yes, right? Not everybody, but most of you would. Okay, so that could be true. That's totally a true statement. Or if someone says to you they're not a mom and you assume that they're a man, could you be true in thinking that? Yes, also equally a true statement. Okay? So it's sort of this statement that we assume people are telling us the truth unless we have justifiable reason to believe that that's not. And if they told us that they are a mom and we said you're a man, that would be justifiable reason to think that we're off our rocker, right? Okay, that wouldn't work. Okay? So this one feels a little bit awkward because it feels like that if you start out with a false statement, how could the result then be true? Well, because you have sort of not enough information to make a claim that it is true or false. So the assumption is that it's true. So with a true-false statement, if it starts out true, true, it's true. Or if it starts out false, it's true. The only line that is not true, I didn't mean to mark that out. Let me try that again. I meant to highlight it. The only line that is not true in a true truth table for a conditional is the line that starts out true and it ends up false. That's the only one. It's the only one that's a false statement. All right, so you're going to do some examples with some if-then conditional statements in your homework. We're going to write some symbolic, we're going to change some symbolic things into words, into symbolic. All right. Let P be the statement, you build it, and Q be the statement, they will come. Does anybody know what this is from? Field of Dreams. There's going to come a semester that I'm going to ask this question and nobody's going to know it because this is an old movie at this point. Field of Dreams is the movie. All right, so let P be the statement, you build it, and Q be the statement, they will come. And what we're going to do is we're going to take a statement as it's written and we're going to write it in symbols. And this first example is exactly the example that I referenced earlier where the if shows up in the middle of the sentence, right? So you have to start where it starts with if. If you build it. That is the hypothesis. That's where we start. What symbol is represented by you build it? That's P. So this statement, it starts out P with an arrow. I know that the P is at the end. Doesn't matter. So is the if. It's where the if is that's associated with the hypothesis. If you build it. And again, I know also that doesn't say the word then here. There is an assumed then. It's not always said when we use English. If I even said this in the other order, if you build it, they will come, that actually still works. But it's also true to say if you build it, then they will come. Right? The then doesn't really serve a lot of purpose, but it's understood to be there. So this is P arrow Q because they will come was what Q represented. Q was they will come. Now the second statement here on part B, the if is at the beginning, so we don't have to worry about like altering what feels like the order or anything like that. We just start with where the beginning is because if is at the beginning. This is if you do not build it. What would be if you do not build it going to be? That's the negation of P. The word not, right? Made it the negation. And this has this if-then structure, so you've got the arrow. And then it says they will not come. That's a negation of Q, right? Tilde Q.
Wait, so on the first one,
Mm-hmm.
how do you know that it's not like Q to P because Q is they will come and that's first? I know you explained that.
It's because of where the word if is. The part if is where we begin our sentence. If represents the hypothesis. The hypothesis comes after the word if. So the coming after the word if on this one is you build it. So that's the part that would actually be our hypothesis for our statement.
First, I mean, whatever comes after if is first.
Correct. Whatever comes after the if is our hypothesis.
So it could technically be Q arrow P.
You could have one that's a Q arrow
part
P.
came after if.
Yes. Yeah. Yeah. If this question had said, if they will come, then you build it. Sure, because the if then would be associated with them coming. That's fine. There's nothing special about the if and the then in this particular statement being in the specific order. It's just the if is associated with the statement that
So it's always
conjunct-
P then Q.
connected to. It's not always P then Q. It depends on the structure of the sentence.
Well, do we write it as it's always P then Q?
Okay, let me write you another sentence. Let's say that this sentence says, if they come, then you will build it, or did build it. I don't care about the UILD. I don't care about the English structure of the past tense or anything like that. That's not my concern. My concern is where the word if is. If in this one is actually associated with they will come. I've done it twice now. I wanted to stop there. Okay, if they come. Well, what's they come? That's Q. Then you will build it. It's P. Okay. The hypothesis is simply what's grouped with the word if, and it comes first, no matter where it shows up in the sentence. Okay, is that all right? Okay, I have another one. We're going to go the other direction. We have some symbols, and we have some language associated with them, and we're going to write the sentence that they represent. P be the statement, God loves me, and Q be the statement, I am a sinner. Okay, so the first one, what symbol is that that's occurring between the P and the Q? It's and. So we're going to first write down what P represents in sentence form or in word form. What is P? God loves me. What would I write down next? And. Okay, that's the symbol in the middle, and. And then the Q is I'm a sinner. So this is the language form of those symbols. Now, the next one has the arrow in it. And there's no reason to make things complicated if the arrow's at the beginning. We can always just start with the word if. Okay, there's nothing that says we should really just try and make things more complicated on the grader. Please don't do that. Okay, just start with if. It's an if-then statement. Let's start there. Okay, this one says tilde P. Yeah, that's how that would start. If God does not love me. Yes, it's sad and it's not true, right? If God does not love me. Okay, that would be the tilde P part. And the next part would be then. What? Yeah, I am a sinner. That's the way that that structurally would be written. Now, I actually include this in here because I want you to recognize that just because we're writing down sentences doesn't mean the sentences we write down have to be something we believe in or that are true. It's not the point, right? The point is that the structure matches the logical structure of the symbols, okay? And it does. This is the language form of the logical structure of those symbols. And it is a false statement, right? Yeah, this is weird. This doesn't even work because we know that part's wrong right there at the get-go. Okay, a few other things. Conditionals have the original statement, and we have been writing it as our default as P arrow Q. There's nothing special about me writing the P beginning and the Q second. It's just that's the standard way to write it. Okay? There are three statements that correspond to the statement P arrow Q. The first one is called its converse. So if you have a statement and then you're creating its converse, what the converse is that the converse restructures the statement in the opposite order, Q arrow P.
That was like the number C we did, right?
Much like it after we compared it back to A in that problem, right? So if you had a statement that says, if I'm a mom, then I'm a woman, then its converse would say, if I'm a woman, then I am a mom. That's what the converse would say. Okay, it's just changing the order. That's all it is.
That's not necessarily always true.
It's not always true, and we're going to talk about when it's true actually later. Not always true. Now an inverse, you've heard that word in mathematics before, is similar to the original statement because the P and the Q are in the same order, but what happens is they're both negated, like this. So again, if I did that one where I just did before, if I'm a mom, then I'm a woman, it would say, if I am not a mom, then I am not a woman. Again, that's not a true statement, right? So clearly both the converse and the inverse create something that's not always true. That's what they do. The contrapositive, however, takes the statement and it both switches the order and negates it. So you end up with tilde Q, arrow, tilde P. And in my example, that would say, if I am not a woman, then I am not a mom. And that would be a true statement, right? It would. And we're going to explore in your group work which of these are equivalent to which. And you may already have some sort of a inkling in your mind what you think is going to happen when you do that. But I want to show you one other thing. We're going to do one with some language. We're going to create the converse, the inverse, and the contrapositive for this statement right here. If I'm a monkey, I have a tail. Okay? So the first statement is already written. So this is the P, arrow, Q statement. We're going to create the converse. So what does the converse do? It switches it around, like the order, right? It's all about the ordering. So how would it start? If I have a tail, then what? Then I am a monkey. Okay. The first statement, as it was originally written, if I'm a monkey, then I have a tail. Is that a true statement? It actually is. Biologically speaking, that's a true statement. How about the second one that I just wrote down?
Not necessarily.
Not necessarily. Can you give an example?
A dog.
A dog, a cat. Okay, we're going to talk more about this in a minute. That's a good way to start. Next one, inverse. What does an inverse do? It negates both statements, but it keeps it in the same order. So it will start out with what? If I am not a monkey, then I do not have a tail. True? False. Yeah, it's a false statement, right? Your dogs and cats that you just mentioned a minute ago will work on that example as well. And the last one is the contrapositive. Sorry. Okay, what do you want me to write next? If I do not have a tail, then I am not a monkey. What do you think? It is also true. And we're going to do one thing before you guys get into groups. Any idea what it might be? I have a YouTube video for you to watch.